My name is Michelle, and in my last video, I had showed how that I had built an I2C EEPROM circuit board and had it built for me. And then I showed how that I was able to write to the EEPROM through just kind of hard coding the information over on an FPGA, and then I also showed how that I could read and write from the PS side of the FPGA using the I2C port attached to the microcontroller. Well, today the goal is to show that I can read and write with the command being initiated from the PS and then going from PS through AXI to the PL, and then using my hand-coded I2C to write and read to the I2C EEPROM. So today, usually I would show you the results at the end, but I'm going to go ahead and show you the results up front, and then we'll try to explain some of the things that goes on. So as you can see in my screen right now, I had just run it, and it says that I sent a command over. Basically, it turns out on this I2C, you have the basic command that says it's a read or a write message. Then you got to send the high 8 bits of the address, and then you send the low 8 bits of the address, and then you send the data for a write. And if you want to do a read, you send a write command, the high address of what you want to read from, and then the low address of what you want to read from, and then you would read from that result. And I will show you the code that does that in the future here in a minute. But for now, I utilized, actually, let me get my cursor over here, although I'm not sure you see my cursor, which is terrible. It says I told OBS to show my cursor, but for some reason it doesn't show it. So I'm going to try highlighting some things maybe. There you go. So this would have been, in essence, the command message, but since it's pretty much the same every time, I went ahead and utilized this to tell me to set a write or read bit. Since on a read you send a write message. So I went ahead and used that to send a write and a read bit, and then literally another bit to be whether it's valid or not. So in this case, of that the 8 bits that are here, or even I'll go ahead and say these 4 bits, basically bit 1 is 0 is a write and 1 is a read, and then bit 2, or I should rephrase, bit 0 would be the write and read, bit 1, which is technically the second bit, would be 1 would mean that it's valid. So in this case, 2 is a 1-0, so it's valid and a write. And then of course then here is the upper half of that address that we're going to write to. Here's the lower half. I know I can't get my cursor right. The lower half of that address that we're going to write to. So we're basically writing to address 1. And then we're going to write we wrote the character 74, which is a T. All right. Then I basically sent in another command to tell it it's no longer valid anymore, because I still got to work on how to tell AXI to do a valid statement versus not a valid. I haven't figured that part out yet, but I'm working on that. And then basically my next command I wrote was this 3, which is a 1-1 now. That means it's valid and it's a read. So then again, the top 2 byte of the address, the lower byte of the address, which is address 1, and then this A1 is the actual read command, which is 1010, which is A, and then 0001, because that's where the read write bit is on the command, and so therefore that's telling it to read. And of course then my code would have then sent the command over, and then it would have gotten some data from the EEPROM, and then I'm shipping the data back cross AXI back to the PS side and telling it what the response is, which in this case, so the next one here, I just wrote a 0 again to tell it not valid, and then the response comes in, and it says that the response was a T, and it was a 74, and then of course it said, well, it successfully ran. What I'm going to do, just to prove that I didn't fix this or make it up, is I'm going to go ahead and change my code to write basically, I've been going between the character A and the character T just randomly. But 41 is the character A, right? So I'm changing my code of the write command I'm sending in right now. Eventually I can have some kind of ability to type in an actual address, but right now I'm just hard coding it into the C code on the PS side. And this is my C code on the PS side. And anybody who knows the microcontroller code, you can tell this is that code. Oh well. So I'm going to go back into my SDK. I'm going to rebuild the project that I just changed, and then I'm going to literally tell it to run on the FPGA. So it's going to basically it's going to do whatever it does. Then it'll start trying to transmit to it. There you go. It's literally programming the FPGA. So here was a screen that we were looking at a minute ago, and now, so now I sent the command to write a 41. Then I told it to read, and then so the answer I got back was, well, the response was A, 41. So there you go. So I've now shown you that all the work I put into getting this to work, it actually does work. So now let's go and look at what I did in order to make all this happen. And like I said, the very first part is that I had to write, obviously, the I2C logic that literally would break a message up, such as like this one, and send it out serially to the I2C EEPROM in the format that it liked. And of course, like I said last time, we went through the spec of the I2C EEPROM, and we talked about the start condition. Then we talked about sending the command bit. Then we talked about sending the high address, the low address, and then either sending data or getting response. Then we talked about the stop bit scenario, and I went through the waveform and everything like that. So I'm not going to go over that necessarily too much anymore. This one is more, how did I get all this into the PS side? Well, so basically you can see there was my master code, and in my master code, it's pretty much doing the state machines that does what the transfer, to serial. And I have basically the ability to identify what master is, the ID for the master, and then the maximum bytes that you're sending. In this case, 4, because 32 bits makes up 4 bytes. And right now we're just sending in one command. Basically a clock reset. Here's our command in, a valid, which I still got to work out how to do that in AXI, on the IP that I didn't write. And then here's my output. And then basically here's the communication through the SDA and the SCL for I2C communication bus. And the actual bus connection is in my top. And if you come down, you can see where here's where I'm instantiating my master. And basically, you got to realize that, like, for instance, the PS side uses a 50 megahertz clock, but we needed a 400 kilohertz clock. But because of the fact that I was using on my master 1 clock cycle for a high and 1 clock cycle for a low, I needed an 800 kilohertz clock. So basically, I took the clock and I reduced it down to an 800 kilohertz clock, which is why that's my input to my master, as you can see right here. And I realized you guys can't see my cursor, so I got to be a little more cautious of that, or conscious of that. Oh well, and so then, but how do I get it to the PS side? That's the important thing. Well, I went ahead and I'm in Vivado now, and I have the project open. I'm going to open up a block diagram. So creating the block diagram was pretty simple. No big deal. At first, I actually tried to put my code for my I2C into the block diagram, but I kept running into some problems. Not sure why. You know, it could be a flaw of Vivado. I'm not 100% sure. It should have worked in my mind. So what I ended up doing is I ended up creating a block design. I find it interesting how they got this. Let me see if it arranges nicer. Huh? Well, I don't know if it did or didn't. Um, Pretty much a block design with the GPIO connectors and connecting up the, like in this case, this is my GPIO out. And then basically I have my GPIO in, which is going to, so my this output goes to my I2C stuff. And then this input comes from my I2C stuff for my response. And then that's wired up. So each one has their own GPIO port that we're connecting to. And then they go through their own interconnect, which is interesting that it created. Well, I'm not sure whether I couldn't have used just one interconnect and only one port or not. The tutorials I was watching on how to do this, they were using two ports, but I think that was mainly because on the address editor, it was easier to use on the guy who taught the one I looked at, it was 4,000 and then 8,000. I'm not sure why the number was 4120 on mine and 8120. Not 100% sure why. Maybe how big I've made something. Oh, probably the 64. No, I'm not sure why. But oh well, it was easier to just change the number here than with he was using a counter type something, and so it was easier to change that number than to like adjust for two GPIO outputs on one bus where it would have been like a different number but on the same like 4,000 realm. And so I think that's why he did it. I mean, maybe there is a legitimate reason to go ahead and have literally, oh, come on, two ports and literally using two masters. So I did what he did just so that I wasn't taking a risk of it not working. I could tinker with it and find out the answers on my own if I wanted to, and that's a whole nother video if I wanted to do that. Anyways, so it's a pretty simple design. You got your processor outside of the processor where literally one master is going over to this interconnect, and that interconnect is going to the GPIO, and then that GPIO is going out. Then you got, like I said, you got your in, which is going to this GPIO. That GPIO is going to this peripheral, and that peripheral is going to the other master. And that's how we're going to communicate within the master. And of course, as usual, anytime you have a clock and a reset, the block design creates a reset, a system reset controller. Oh well, okay, so basic block design. All right, well, so like I said, at first I did try to connect my master directly to this, but it didn't work well. So what I ended up doing is I ended up taking, if you go look at the source down here, I ended up taking my block design and creating a wrapper. And then I had my master, and I created a top that instantiated both of these and linked them together. And so we'll go look at that right now. So here's my top, as we were saying before. Remember, here was my instantiation of my master, and of course my clock divider to get the clock I needed from my master. And then you'll see here is me instantiating that wrapper, the I2C wrapper, which has the DDR access to DDR RAM, and then some maintenance stuff that it does. And then here is my input for my GPIO, my output, and the clock I needed so that I can control my master with and my reset. And so I've instantiated it, and so I basically told it to create an output to uh, like it would have had it been the normal wrapper, but with the signals that I needed, which were setting the address of the EEPROM itself, setting out because I have an LED for whether it's reset or not reset. And then here is my I2C bus, which SDA is an in-out port, which always has to be on your top module. So I linked basically the block design to my master so they'd communicate. And so that's it. That's basically the technology here. I'm just being able to tell my top what frequencies I'm using. In this case, I'm using the PS clock, and so it's 50 megahertz, and I need basically in the end I would need a 400 kilohertz clock. So, and you could always set that and change to what you want to use. If you're like, for instance, if you're going to use the PL clock, in this case it's 125 megahertz, and so you would send in that piece of information. Oh well, so let's go back to here. And so like you can see, here's my top module and it's instantiating. And so I built the information and compiled it, and then I exported the design. Then I imported that design into Vitis. As soon as it was imported, I basically I created a platform. I'm using a Zybo Z7020, so it built based on my platform I built. It built this information with the BSP attached, and then instantiated my code. So let's go take a look at the code here again. So basically, I'm just telling it that we are going to use the two GPIO port IDs. These are the IDs for the two ports. I'm kind of setting up some, like for instance, my write bit was bit 28, my valid bit was 29, which you could see in my master code. I did that. I pretty much set it up and said, if it's a reset, well, it's in a different location, but the reset is mapped to that. And then here we're saying bit 28 is my read write. And then here's, like I said, the A that would normally be there, but it's there every time. And then so it's basically A plus my command. And then here's my high bits, here's my low bits, and then here's my actual either write data or the read command. And then, of course, like I said, throughout here you got the logic, and I just realized you can't see my pointer again. I'm sorry. You should be able to see it there again, highlighting. Here's the read-write scenario. Here's the command bit. Here's the low. The high. Here's the low, and then here's the either write value or the read command. And then, like I said, the state machine that does all that work. So basically, I've created variables for each two GPIOs that I just realized you can't see again. GPIO 0, GPIO 1. My write command, I put in the command that I needed. And basically I'm just telling it to make sure this is the command, but make sure that the write bit is a 0 for a write and the valid is 1. And then I have a read command. And then make sure that the write bit is a 1 and that the valid bit is also a 1. That gives me, which is my 3, and that is actually this bit right here that it's talking about. All right, so then I instantiate the platform. I go out and look up the config and initialize both GPIO ports for GPIO 0. Getting my GPIO 0, my GPIO 1 addresses and everything instantiated. This one here is just clearing the screen, and then I'm testing, and then so basically I set my directions for my out for GPIO 0 is output for my write, and GPIO 1 is a 0 for input. And then basically I tell it to do a discrete write where I do my write command. Then I tell it to do another discrete write, but with a non-valid command. Then which is I'm writing to the EEPROM and then setting it not valid. Then I do a read where I send out, um, again, GPI 0, a write command, but it's a read command, but it's kind of a write command that has a read command at the end. And then I do another non-valid, so it doesn't know it's valid. And then I read from GPI 01 because that's where my input's coming through. And then, of course, I just tell it to output the response to where I'm going. And then I didn't do any checking, so it just says successfully ran. But I could have said, well, they match. But in this case, we can visually see that it matches. And of course, like I said, when I ran it, I sent over my write command with 41, and then I read it, and I got my 41 back. And so there you go. It works. Um, so I have actually written an I2C Master and that works in the PL side. I've written the commands in the PS side to initiate it, and of course it communicates via AXI bus to the PL from PS side to PL side, and then it initiates the commands to the EEPROM through my master I2C code. And there you go. There it is. I hope you enjoyed the video. Probably my next task is probably doing a block write and read, because right now this only writes and reads um, one address. So I need to probably work on that. Then maybe working on a slave, or who knows what my next project is. But I hope you're enjoying this. It's basically I'm trying to learn how to do this and then I present this information to, well, one, prove I learned it and I got it to work. Two, to share it with my friends. And then three, hopefully one day somebody might want to hire me at doing this and they can see that, oh, wow, I'm showing that I know how to code in VHDL. I'm showing that I know how to use it, uh, the PL side, and program it, make it work. I know how to use the PS side to initiate the commands and communicate between the two. And I'm using the tool. Last time I believe we did an ILA. I mean, so I already have proven I know how to use an ILA. So I think for the most part, I'm presenting most of the requirements to be an FPGA design engineer. Now admittedly, there are, you know, most companies are hiring fast speed type stuff, and this is very low speed. I'm very aware, but for the most part, the mental power to be able to to create an I2C driver. I mean, that was more difficult than AXI. I mean, I did an AXI bus. That was easy. The timing that was required to do this master code, I mean, that was more complex. It was, I mean, in the end, I made it smaller. If you saw the code before, I mean, this thing had a lot of states and it was, um, you know, drawn out, trying to get the timing right. And then once I kind of got all that working right, I combined it into basically just uh, 1 byte states machine. So if you look at my state machine, you can see that I have my idle, my start low, start high, then my input low, input high, my act low, act high, and then a read, and then stop. So I don't have all those other states that I had before. And so, I've so I'm showed this was much more difficult than AXI. And so I think I'm proving that I've got the mental power to be able to do the work. I just need somebody now to hire me. So, oh well, thank you for your time. I hope you got this far. Most people don't. But if you did, thank you. I hope you enjoyed it. And I will post my next video on whatever the heck I learned next. Okay? Thank you. Have a good day.